Serving large generative models, like large language models and multimodal transformers, is one of the most demanding challenges in modern cloud computing. End users expect lightning-fast responses, measured by two key metrics: time to first token and time between tokens. These are service-level objectives, or SLOs, that define the user experience. But from the provider's perspective, the goal is the opposite: minimize GPU costs, maximize utilization, and reduce energy consumption. This tension is real, and it's getting worse. As inference workloads grow more dynamic, with wildly varying input lengths and unpredictable traffic patterns, traditional provisioning strategies are failing. Static provisioning, sizing infrastructure for peak load, leads to massive underutilization. On average, cloud providers see only 50% GPU utilization for text workloads and 39% for multimodal tasks, even when they're provisioned for the 95th percentile of demand. The root of this inefficiency lies in how we think about scaling. Most systems treat the entire model as a single monolithic unit. When traffic spikes, we scale up entire model replicas, loading full 70B parameter models onto new GPUs, which takes over 10 seconds just to initialize. And when the load drops, those GPUs sit idle burning power while we wait for the next spike. But here's the insight: large generative models aren't monoliths. They're graphs of interconnected operators. Each layer in a transformer is a DAG of operations: attention, linear transformations, normalization, activation functions, embedding lookups. These operators vary dramatically in their compute and memory footprints. Through detailed characterization across diverse models, QN2-7B, Llama 3.8B, Mixtral 8x7B, and QN2, 5VL, we found that operators are fundamentally heterogeneous. Attention, for instance, scales quadratically with sequence length, OL2D. That's a killer for long context inference. Meanwhile, lightweight operators like layer normalization grow nearly flat. And some, like fused MOE layers, are compute-heavy at short sequences but scale poorly as context grows. This heterogeneity means that scaling the entire model is like upgrading a whole car just because the engine is overheating. You're wasting resources on parts that don't need help. So we ask, what if we scaled not the model, but the operators? Our work introduces operator-level autoscaling, a framework that treats each operator as an independent unit for resource allocation. Instead of replicating full model instances, we dynamically scale individual operators based on their real-time sensitivity to workload. The result? We can meet the same SLOs with up to 40% fewer GPUs and 35% less energy. Or under fixed hardware, we achieve 6 times higher throughput while reducing energy by 5%. How does it work? First, we build a performance profile for every operator under diverse conditions: batch size, sequence length, request arrival rate. We use CUDA profiling to measure kernel-level compute time, memory usage, and communication overhead. We also model queuing behavior using MMR theory, because latency isn't just about computation, it's about waiting in line. For example, attention operators become bottlenecks at high sequence lengths. But at short sequences, it's the linear layers or MOE experts that dominate. And some operators, like normalization, benefit disproportionately from batching, not more GPUs. So we don't scale blindly. We identify the true bottleneck on the critical path and scale only that operator. We adjust replication, batching, and parallelism in real time, using a greedy algorithm that iteratively improves performance while minimizing resource usage. But scaling isn't just about adding replicas. It's about where you place them. When multiple operators run on the same GPU, they compete for resources: streaming multiprocessors, SMs, memory bandwidth interconnects. This creates contention, and if not modeled, can actually degrade performance. So we introduce a contention-aware placement strategy. We use profiling data to estimate how much interference each operator causes when co-located. Then we assign replicas to devices in a way that balances efficiency and cost, preferring to co-locate scaled operators on existing devices when safe, only provisioning new ones when necessary. This is a shift from model-level auto-scaling, where every replica gets its own full GPU set, to a system where multiple operators share devices intelligently, just like a well-orchestrated orchestra. We evaluated our approach across production-scale traces from Azure and Mooncake AI, using real-world workloads with fluctuating QPS, sequence lengths, and model types. The results were striking. At moderate sequence lengths, around 4K tokens, GPU savings peaked at 40% for MOE models, 30% for dense models. Energy savings reached 25%. Memory savings hit 60% or more at 32K tokens, because we didn't scale non-bottlenecked operators. And when we looked at prefill versus decode, the difference was even more dramatic. Prefill stages, being compute-intensive and bursty, saw 2-3 times higher savings than decode. This suggests that prefill, decode disaggregation is not just a good idea, it's a necessity. And operator-level auto-scaling makes it even more powerful. We also tested under varying QPS. At moderate loads, around 4100 QPS, operator-level auto-scaling delivered the highest gains. Why? Because it avoids over-provisioning during bursts, while still handling queuing delays efficiently. Even for the largest models, QN2-72B, savings peaked near 50% in energy and memory, proving that scale amplifies the benefits of fine-grained control. And how close is our greedy algorithm to optimal? We compared it to a brute force oracle. On average, we're within 8% of the theoretical minimum, with a fraction of the computational cost. So when should you adopt this? Operator-level auto-scaling shines when workloads are dynamic, heterogeneous, and latency-tolerant. It's less effective in systems using megakernels, where all operators are fused into a single monolithic kernel, because there's no granularity left to exploit. But in modular, efficient serving stacks, like vLLM or future systems, it's transformative. It also complements existing trends: prefill decode disaggregation, encoder LLM separation, and expert as a service architectures. We're not just scaling models, we're rethinking the unit of scaling. Looking ahead, this work points to a future where large-scale inference isn't about provisioning for worst-case scenarios. It's about real-time, operator-aware orchestration, where each kernel gets exactly what it needs when it needs it. By shifting from a model-centric to an operator-centric paradigm, we can finally close the gap between user experience and provider efficiency. The era of monolithic scaling is ending. The future is fine-grained, adaptive, and intelligent. And it starts with the operator,